Hello again, this is Steve Gibbs. Teach electrical engineering at the University of Texas at Arlington. Today we're going to look at derivatives as they're applied in electronics. So let's take a look at, and we're just barely going to scratch the surface, but let's get started. Okay, since we're talking in electronics, let's start with the ideal black box. Have no clue what's in it. What we know is that we have two terminals, a positive and negative by definition, and we apply a voltage. Now this voltage, notice that this is lowercase v varying in time. So this is not a constant anymore. At the same time, this voltage produces a current into the device, I of t, again varying with time. And from that, we'll start defining some definitions. What we're going to see is that there is a derivative involved in defining the voltage. The voltage is a change of electrical potential energy, that's our W, with respect to or as a per unit of charge, which is measured in coulombs, and dW dQ, the derivative of the electrical potential energy with respect to the charge, is volts. Similarly, our current I of t is defined as the change in the charge Q with respect to time. So the change of charge or coulombs with respect to time, seconds, coulombs per second is a definition of amps. Power is the product of the voltage times the current. So as we look at the power, we've got dW dt. Now let's look at that a little further. To look at the change of potential energy per unit of time, we've got to break that into two parts, as you saw previously. We've got the electric potential energy per unit charge and the charge per unit of time, because this is volts and this is amps. Well, let's look how we got there.
In order to work on the chain rule for derivatives, we need to have a function of a function. In this case, we're working with the function being sine of 2 pi t, but this function within a function is we have a sine of a value, but t is not by itself, it's a function 2 pi t. So we'll call that sine of g of t, where g of t is equal to 2 pi t. So the process is to take the derivative of the sine first, and then we take the derivative of g of t. So f of t is the sine of g, g of t is 2 pi t, and we'll take the derivatives of each. The derivative of the cosine of g, or the derivative of the function, is the cosine of g, which is the derivative of the sine, and 2 pi, which is the derivative of 2 pi t. And we multiply them together. So here's our function. The derivative of our function with respect to time is 2 pi cosine of 2 pi t. So now let's go back and look at our original problem. In this situation, we have the power, P of t, is equal to the electrical potential, W of t, with respect to time, and that's measured in watts. So this electrical potential energy with respect to the derivative of t, we've already seen as a two-part process, because it's the derivative of the electrical potential energy with respect to the charge times the charge with respect to time. But when we defined these before, we said that that represented volts, that represented currents, so that our total function is the power is equal to the voltage times the current. To this point, we have looked at energy dissipating devices, such as a resistor. A resistor dissipates the energy that's applied to it as heat. Now we move on to two energy storing devices. The first is an inductor. An inductor looks like a coil of wire, or is a coil of wire, and as current flows through a coil of wire, it builds up a magnetic field. So energy is stored in the magnetic field. But it's also a nonlinear function. So in our case, if we apply a current of 10 times e to the minus 5t, that's its waveform, and we use a 1 millihenry inductor, then what we'll see is that the voltage across the inductor, V of t, is equal to L, the inductance, times the derivative of the current with respect to time. So let's take a quick look at that. The derivative of the current with respect to time is going to be 10, our constant, times minus 5e to the minus 5t, which is the derivative. So putting that together, we have minus 50e to the minus 5t. Now we can put the pieces together. We take that minus 50 e to the minus 5t. We'll add the inductance, L, and put the process together. So the voltage across this inductor is minus 0.05 e to the minus 5t volts. For an inductor, we've looked at the mathematical analysis. Now let's take a real quick look at the waveforms that those mathematical analyses produce. The current through the inductor starts at time 0, starts at a negative value, and then as time progresses, it decreases towards 0, and it arrives there around 1.4 seconds. The voltage across the inductor, because of the rapid change of current, is decreasing, and it starts at 10 volts, and it drops to 0 about the same time that the current goes stable. Because remember, if the current's not changing, then the voltage goes to 0. So this shows us the waveforms for the inductor. So far in our focus on derivatives in electrical engineering, we've looked at the basic concept of voltage, current, and power. Then we looked at the application of voltage and current to inductors. The next step is going to be to look at the voltage and current across a capacitor, or current through a capacitor, in the derivative-based analysis. So come on back and we'll talk about capacitors.